And welcome back. Now, you may remember a few videos ago we talked very briefly in passing about H-Bridge Motor Control, and I said that's something for a future video, and guess what, this is it. Here, this little unit here, this is in fact an H-Bridge controller, but it's all a bit magical, isn't it? I think we want to get down to a bit more of the detail, and to make it a little bit more fun, I have this little unit here. Couple of motors, couple of wheels, bit of a base plate, batteries and so forth. I'm not really into sort of model cars or robotics, but it sounds like it could be fun, especially if we add in something like this. This is an ultrasonic detector, well, sender and detector, to avoid obstacles, just to add a little bit of fun to that. And well, and eventually, when we know enough about it, this is the useless box where it all started from. And oh look, there's one of those motors in there. What we said was that if we control this a little bit better, we can make this useless box just behave that little bit more like a fun unit. Now, the H-bridge I'm using there, whoops, this little tiny thing, is quite different to this one here. This one here is obviously meant for high current. It's got a big heatsink on it and stuff, and indeed that's the sort of thing you may well find you'll be using for this. We'll find out where I got all this from, plus that in due course, but let's think about what H-bridge control really means, because it sounds very exciting and you know, something a little bit more complicated than what it should be. But what we actually are trying to solve the problem of, you have an Arduino, you want to turn a motor on, but not just on, you want to turn it clockwise and anti-clockwise. How do you do it without A, blowing up your Arduino, and B, how do you get that backwards and forwards control easily sorted without convoluted relay use? Right, first of all, a tiny bit of theory, and I'll draw out a couple of pictures just to make it a little bit easier. Okay, that's what's coming up next. And so to the theory. Now, you may have noticed that I've actually started to build this up while I was contemplating how to describe the circuits best, but don't get too excited, because we're not actually going to be running this particularly as part of this demo. We're talking about H-bridge motor control, and yes, we'll be turning at least one of these motors around, but we won't be connecting up this ultrasonic sensor just yet. That's potentially for a different video altogether, but that's what we're aiming for. So let's think about the theory then of why we need an H-bridge to turn one of these wheels forwards and backwards fairly easily, well, very easily. Let's make no bones about that with an Arduino. Okay, so let's first think about the humble transistor, something like this. Now, this is a 2N3904, I think, and as you can see, I've drawn the connections on the bit of cardboard it came in. But in general principle then, any NPN transistor behaves pretty much in the same way. So if we have the Arduino here, it has some kind of GPIO output here, and that would go via a current limiting resistor into a standard NPN transistor like this. Now, the emitter would normally go to the ground, and the collector would go to the motor like that, and that would then go to your positive supply. Now, let's not get too hung up here on the fact that this positive supply is probably going to be a separate positive supply compared to what's being run on the Arduino. In other words, to try and run the Arduino on that same supply would probably not be advisable at all. One, because you've got lots of noise on here, and B, because this may very well be a higher voltage than what the Arduino is really expecting. Anyway, here we have the motor. Now, just for completeness and to avoid all the comments, we'll put a protection diode here just across the motor. What that does, that stops any spikes and stuff coming back down the line and either destroying this transistor and potentially creating even more noise on this line and upsetting things. Now, this is all well and good. So in the Arduino world, we say set this pin high. Okay, now this transistor, remember, it's a current amplifier, so whatever current manages to get through this resistor here is going to be amplified many times by allowing current to flow down here. So let's take a very simplistic view. We've gone high permanently, okay, just digital write high on that pin. So this motor requires, I don't know, let's say, well, a bit like the one I've got on my desk, about 300 milliamps. To get 300 milliamps from whatever voltage we're supplying means that this transistor here has got to dissipate quite a bit of power. How then would you make that motor go into reverse? We now want effectively this motor to be switched the other way around. So what is the positive of the motor here and the negative of the motor there? We want it flipped, don't we? So we can go reverse. How do we do it with this one transistor? Well, the answer is you can't. That's the problem with it. If you just want to turn a motor, this is fine. Well, it's not fine really. We'll come on to that. But you can't go in reverse. So that's a dead showstopper. So whilst this is a good way of turning on LEDs and perhaps relays and stuff instead of a motor, it's no good at all for things that need to change the connectivity of whatever it is you're connecting to here, the polarity. Okay, right, let's go to Mark II. Right, here we are then for Mark II, and this time we're going to use a MOSFET, which everybody who uses an Arduino eventually comes to realise that MOSFETs are the way to go. Now, let's state this up front though, we need a TTL level MOSFET. What does that mean? That means the gate only requires 5 volts. What's the gate? Well, let's come on to that then. Let me draw a MOSFET diagram here. Let me get this right. So that's going to come in like that, and then we're going to have at least a couple of lines like that, and somewhere in here there's a diode or something, I don't know. That will do. So that's the drain, that's the source, and that's the gate. The gate is effectively the switch. Now you want that there to be 5 volts because that there is 5 volts. All that does here, this resistor, is limit slightly the current that can come out of the Arduino. You're protecting your Arduino basically. Okay, let's assume this is an Uno. Okay, now what happens with a MOSFET and why is it any better than what we've seen before? Well, the source goes down to ground, the drain then goes back up to the motor, to the plus whatever it is, and yes, once again we'll have a little protection diode across here just to stop all those nasty spikes. Now, why is this better? Well, the one massive advantage is that this MOSFET is going to have a very low resistance when this gate goes to 5 volts. In other words, when this switches on, it really does switch on. You don't have 40 ohms here. You might have in a slightly poorer quality MOSFET 0.2 ohms or 0.02 ohms. I've got some. Now, as you can see with our power dissipation, if we've got 12 volts and 0.02 ohms, in our little diagram again, VIR, we can determine the maximum current that's going to allow through. So 12 divided by 0.02, that would be something like 600 amps it would allow through. Well, of course, your motor won't need anything like that. We've said in our example, we're assuming this is 0.3 amps. So this is not going to have any perceptible effect at all on the performance of that motor. Connect it up, say 12 volts, if that's what it requires, and the resistance is so low between the drain and the source that it will operate at absolute full efficiency. Hurrah for the MOSFET! Oh, hang on a minute though. We said last time, if that's the positive of the motor and that's a negative, notional, how do we reverse the polarity with this? And the short answer is, you can't. Not with this circuit diagram anyway. Okay, now this is great again for turning on motors that only need to go in one direction. Brilliant, and you probably wouldn't even need a heatsink on this. And relays, well, you probably wouldn't need a MOSFET for a relay, but if you did, or something that required a bit more current, this is brilliant, but not for something that needs bidirectional travel. Okay, so part 3, the H-bridge. Right, before we draw a real circuit, let's think about how we could turn the motor in reverse and forward just from a single supply. And figuratively, what we have then is a motor in the middle. Now that's got to be connected, if you like, one side's got to go to positive, one side's got to go to negative. You switch them round and it will go in the reverse direction. So if we had a switch here to the positive, this is plus. If we had a switch here and a switch here, that's the ground. Now as you can see, if we were to close this here and close this here, the current would flow in that direction, would it not? And therefore the motor will go that way round, let's say. Well, if we created another switch there and then another one down there, now we've got to assume that you're not going to be silly enough to shut that switch there and that switch there, because that would create a direct short circuit, wouldn't it, across the power supply. That's why we're doing it electronically. Now last time we said we shut this switch here, which we called A, and the one down there B. Now the motor would go in that direction. Now if we shut C and D instead, the flow would go in this way. Why would that make a difference? Because this side of the motor is now positive instead of the other side, and the motor would therefore want to go the other way. Don't you think that is brilliantly simple? And it's so simple to understand. As long as you understand that A and B are a pair of switches that can be switched, or you can shut C and D, but not both together. And as we said, we're not going to do this manually, although you could knock it up just to prove yourself, but the danger there, of course, is that human error will creep in and you'll connect A and D together, or C and B together, and just have a massive short circuit between your power supply. Not a good idea. That is the principle of an H-bridge, and luckily for us, we've already met a component that will do some of this work for us. Let's see what that is. Right, and in general principle, this is exactly what we're going to do. We'll replace the switches with MOSFETs. Now MOSFETs, low-level voltage MOSFETs, look a bit like this. They are static sensitive. I've destroyed a couple in my time just by touching all the pins and not taking care. So be careful of them. Now you can buy them in hugely long strips. Well, hugely long. You can buy them 10 at a time like this, look. Okay, and remember, low-level gate TTL, 5-volt gate you want. Let's see how this is going to work then. So these MOSFETs are all identical. There's nothing different about them. Now each one of these gates needs 5 volts, if you've bought the right MOSFET, that is. And they're all connected to a different pin on your Arduino. So your Uno might be over here, and you have 5 different pins. Okay, these here are going that way, and they're coming in here and being joined on that, right? Okay. Now what that means is that electronically you'll say switch that on, and the current flow will come down here through that MOSFET, through the motor, down here, through here, and on, and the motor will go clockwise, say. Then you say now switch those two off and switch that one on and that one on, and lo and behold the current will cease immediately and then start flowing this way, and the motor will go in reverse. And that's exactly what some people do. They do build it from scratch like this, and there's nothing wrong with that, except it's all a bit faffing about, really. Well, for my simple taste, it's all a bit faffing about. So what else could we do apart from this? This would work 100%, but using 4 of these not exactly tiny MOSFETs does make the thing a little bit clumpy, but you can actually buy circuit boards with 4 of these already fitted to it, and all you got to do is put your motor on. Well, as I briefly showed you previously, we do have an HBridge control available these days. I've used one in my useless box, the little tiny one, and there's the heatsink one I showed you. Let me just drag those out again. Right, so here it is bolted to the chassis at the moment, and this dual H-bridge, which means it can control 2 motors, one on here and one on here, which means you've actually got the equivalent of 8 MOSFETs in here, which is, you can see now why people do it this way. Not just because it's simpler like this, but because it's a lot cheaper as well. In fact, if we have a quick look where I got this from, you'll see exactly what I mean. Let's go over to the browser. There we are. Now £1.21, that is, for, as it says, for a dual H-bridge. Right. The motors get connected to the sides, left and right usually, and these pins here control what happens. They're connected to your Arduino. So what happens then is that if pin 1 is low and pin 2 is high, it makes the left motor go clockwise, and reversed it goes anti-clockwise. And if they're both the same, that is both low or both high, I would suspect we probably want to set them both low, but then the motor will stop. And you've got 4 pins because you need 2 pins per channel, if you like. It's a dual channel, isn't it? And that's as simple as it is. Now, although you can see I've built this up to some degree already, because I fancied a bit of hardware construction today after lunch. I haven't actually written any code yet, but I think even now you might be thinking, you know, this could be simpler than we think. To control one motor, we'll do it one at a time. All you've got to do is set one of these pins in here high and one low, and the motor will start going round. It will. And more than that, it'll start going round at full speed. Maybe not quite what you want. So we do have to do a little bit of PMW, pulse width modulation. Did I say that right? PWM, pulse width modulation, to control how fast the motor works. Now, I've done a video already on pulse width modulation and exactly how it works and why we want it. But just to recap in 30 seconds, if you were to connect that motor to a 6-volt supply, as we're going to, if you notice on here, it's actually connected to these batteries here. If we were to connect them to the 6-volt supply, the motor starts up instantly. Now, what would happen if you were to get the 2 power leads? Let's pretend these are the 2 power leads here. What would you think would happen if we were to somehow just keep dabbing this, dab on, off, on, off, on, off? Well, yes, you're right. The motor would turn on, off exactly the same, and the car or the motor or whatever would lurch forward in jumps. And that's the principle of PWM. You apply full power to get the full power of the motor, but then you switch it off again, and then you switch it on again. But no, not that on-off as I was doing it. You do it hundreds of times a second. Hundreds. Sometimes you do it thousands. I've got a speed control fan in my computer cupboard behind me. That's over my shoulder there. That's got 2 extractor fans on it, controlled by PWM, and they are pulsing thousands of times a second. So, by pulsing the motor, you get the full force of the motor, the torque of the motor, just for that fraction, say 100th of a second, and then nothing, and then another pulse for 100th of a second, and then another one, and it's the gap between those pulses that determines how quickly or slowly this little model is going to move forward. But it does mean we have a very, very fine control over its speed. Now, I'm not demoing in this video how to build this motor or how to make it move or whatever. As I say, it could be a very interesting little thing to get the ultrasonic sensors working, but we want to get these motors working first and have a little bit of code to do that. Once we've cracked that, I think the rest will just fall into place. So let me connect up some wires to the stepper motor driver here, as it shows it here, and I'll be back with you in 2 shakes of a lamb's tail. Now, without the use of an Arduino at all, we can demonstrate a little bit of what's going on in this bridge device. Okay, so what I've done is connected up just this one motor at the moment, just to prove that it's all hanging together. I've connected 6 volts up. Actually, it's stating 5.9 at the moment, but that'll do, because this is going to be supplying 6 or potentially less if it's going to be rechargeable batteries. But let's not get hung up on that for the moment. So I've connected up the wires to the motor and the 2 inputs, and as I say, it's these that will control the direction of the motor. By default, they are both low. So if I was to bring that one high, it would turn the motor in one direction, and if I was to switch that open and bring that one high instead, should turn the motor in the opposite direction. So let me just take myself off here so I can see down there. Right, I'm going to lift it up so you see what happens. I'm just going to connect it to the same 6 volts. So if I connect the green one first, oh, there it goes. So that's going effectively backwards now. Good Lord, look at the shape of that tyre. Anyway, and now if we connect the blue one up instead to the same 6 volts, and there it goes in the opposite direction. How simple is that? Now, there's not an awful lot of torque going on at the moment. Would it actually be enough to move it? Let's have a look. Oh, come back. Yes, it certainly has got enough there to move it. Let's move it back again. Whoop. Okay, I think we've proven the point there magnificently that yes, this is going to work. I've just got to now get an Arduino connected up, and I think what I'll probably do is put the Arduino, where can I put that? I might put that over the top of the battery. In fact, I might even use this one here. This is from a previous demo where we had a little mini screen. Well, we could make use of that mini screen in here, couldn't we, to tell us what's going on. If I was to put that over here above the battery compartment, just connect it with a high-tech connection called an elastic band, for example, and then I reckon we could power it. Well, for testing purposes, yes, we can power it up with our standard USB, but if we want to ever let this thing loose on the floor and see what it can do, we would have to power it up. Let me see, with I've got one. If we have, yes, one of these, so we'd have one of these to plug into the back for the power. Now I know I'm using a Nano here plugged into a development board, but it's exactly the same as if you had an Uno. So that could go into there for the power, right? So all it's got is a couple of little spring connections at the back here. Very useful for demoing purposes, this. And then into that, if we run the Arduino off a 9-volt battery, just for now, we would need one of these. So yeah, so if I plug that into a 9-volt battery, these two ends, wherever they've gone, well, these two ends into the back end of that. So one in there, one in there. I reckon job's a good one, frankly. Right, looks a bit more cack-handed than it really is, I assure you. But even if I connect all that up, there's still a stumbling block. We haven't got any code. I haven't written any code yet. Now, I think we've said it's going to be pretty easy. Certainly for full speed ahead, we just set the digital pin to high and off it will go, either in a straight line until it hits something, or round and round in a circle, or potentially we could just have it going forward for a bit and then backwards for a bit. But it'd be nice to get the pulse width modulation working, wouldn't it, really, so that we can slowly ramp up the speed and ramp it back down again. Okay, let's get cracking. So I've knocked together a bit of code, and this rather unwieldy mess seems to be hanging together. So this is the Arduino. I'm still running on power, not batteries here yet. Wow, one thing I did discover was the L298 provides a 5-volt out. So we can power our Arduino from that, so we only need one power source. The other thing I discovered was that trying to run these motors on 6 volts, well, you sort of get away with it, but it would be pretty slow. You certainly wouldn't be running a racing car on that. However, although there's space in here for 4 1.5 AA batteries, you can actually get those 3-volt batteries now in AA format. In fact, I've got a couple somewhere. I might even be able to mix and match. But if you had 4 of those, of course, that would bring it up to 12 volts, and I think that would be absolutely ideal. And that's the maximum you can put into here and still have the 5-volt come out. If you put any more than 12 volts in here, say you've got a 25-volt supply, goodness knows from where, but if you did, you've got to take off a little jumper on there and supply your own 5 volts into here to actually power this board. So I think 12 volts works quite well. However, the question is, did it work? Let me just move the camera down a little bit so we can see exactly what's going on. Right, so what I've done with the sketch is simply to read a potentiometer value, a bit like a speed control. You wouldn't do that in real life for a robot car like this. It would just go on its own way. But let's have a look. So it's on 0 at the moment. So if I just turn that... Now, I don't know if you can hear that. Can you hear that whine? Definite whine. That's the pulse width modulation kicking in at a frequency that you can hear. It's about, I think it's about 480 480 hertz, something like that, 460 maybe. But it's really irritating. If you remember, I said that I had a fan in that cupboard behind me there to extract the warm air from the PC cupboard. And that's why I'm having it running at several tens of thousands of kilohertz. So I don't hear anything like this. Because that would drive you absolutely mad, wouldn't it? Anyway, in a model car, I don't suppose it matters too much. There we go. Right, so it's starting now. And as you can see, it's fairly slow. I can probably get it slower than that, actually, if I see. So I can bring it down slow. Now, admittedly, I've jacked it up on a couple of corks and blue tack, just so it doesn't run off my desk. So when it's actually on the ground, you need more power to move it. But it gives you a fair indication of what it's going to do. I've also wired up this switch as a sort of reverse switch, and if I press that, as you can see, it immediately goes into reverse. Once again, that would all be programmatically done by your code. For example, what I'm hoping to do is to wire up these ultrasonic sensors when it detects something within, say, 6 inches, to reverse or to swing round and until it doesn't discover any more obstacles in its path and then carry on. But that's for another day. I think we've have discovered, though, there, that's full power at, what was my 5.8. Let me see if I can just ramp it up to 6. Oh, 6.2. Well, there we are, 6. Made absolutely no difference to the top speed at all. Pretty pedestrian. But then again, for an obstacle type car, you probably do want to run very slowly. So the pulse width modulation bit will really come into its own and bring that right down. So you can crawl around a maze or something like that. And in fact, if I bring the voltage up to 12 volts, well, you can hear it getting faster. There we are, it's 11.9, so it's really whizzing along now, but the pulse width modulation still kicks in quite nicely. Although, not quite as nicely as I'd hoped, actually, because it's... Once you start it, there's that hysteresis, isn't there? So you've turned it off, and then you want to turn it on again, and it has to overcome that initial inertia to move the car along. So it's making quite a racket at the moment, and then it's off. But it does mean it'll be off at a faster speed than perhaps it could control itself down the maze. So let's bring that back down to 6. Well, 5.8 as it happens. Oh, that back wheel's still going, but this front one's stopped. And in fact, that's going to be a problem if you decide to build anything like this, is to keep this thing in a straight line. You'll find the web littered with good ideas on how to do it. And in fact, somewhere on my desk, I took the sensors off. Right, these little sensors, you probably saw them on initially. They go on the other side of the wheel, and the idea is that you shine a light through these little slits and detect that by your Arduino on each wheel, possibly via an interrupt, I would think. 2 interrupts, who knows. And then you can detect how fast each wheel is actually moving, or indeed if the wheel is actually moving. Like now, look, the back wheel is moving but the front wheel isn't, and your logic in your program could detect that and therefore increase the power to one motor more than the other and get them balanced. It's a whole science getting your robot car to run in a straight line, that's for sure. Anyway, I've taken them off at the moment because they just basically got in the way while I was trying to experiment, but they might have to go on if I continue with this project. Right, let me just speed that up because that whining is really irritating. There we are. Right, so that's not bad. Right, here's the code that I'm using for that very, very simple sketch. So what we've defined, remember that the this device, the L298, I'm going to get it in shot, there it is, L298, it's got 2 inputs per motor to control the direction of the motor, and then it's got an input per motor for pulse width modulation. You don't have to use the pulse width modulation, in fact, if you didn't want to. If you just run it on like full speed forward and full speed reverse every time, then you can just ignore 2 of those wires and put the jumper back on. I had to remove a jumper to put those wires on. The direction pin I've got here, that's that little switch that I'm just sort of playing about with, just to show you that the direction bit worked. All pins are output apart from the switch again, which is input. Now here's something you need to take account of. When you read a value from the potentiometer, we read it and it's got up to 10 bits on it, which means it can be between 0 and 1023. As you can see, oh, come back, it's run away. That value you see on the screen there going up and down, so this bit over here, that's what it's reading off the potentiometer, but I've mapped it to between 0 and 255 because that's all you can do for pulse width modulation. Pulse width modulation is only 8-bit. So that's where we map this. That's where we print it, which is what you're seeing over here. And then we say, right, if we're going forward, that is to say we haven't pressed this little button, motor 1A is high and B is low, and the same for motor 2. They sort of parallel each other. We don't want one going forward and one going backwards, although you would do if you were doing like maze stuff by setting one motor going forward and one going reverse. You'd be able to actually spin on the spot very tightly. Very good control, but I won't be doing that here. That's a little bit too much for me. Now if we are pressing this so that the value goes false, then it just switches these inputs. What was high now low, and what was low goes high, and that's the L298 determining what happens there. And then finally we just write the analog speed both to the same motors and say we're not treating each motor differently at all in this little demo, and it outputs the potentiometer value that we read in here but mapped between 0 and 255, 255 being permanently on, 0 being permanently off. And that's it. Now if you were really going to build one of these for maze control or any kind of well, anything other than a demo like I've done here really, then you'd probably want to get to grips with controlling each motor independently, or more independent than I've done it, so that one could go forward, one could go back. You wouldn't want, you know, any kind of potentiometer to control the speed. That'd all be done by this, or I suppose Bluetooth on a phone or something like that. That's pretty easy to do actually. If you look at one of my previous videos about Bluetooth control, similar thing with reverse, you wouldn't have switches or anything like that on here. That'd all be done by the code. Yeah, and then of course power it up in here with the 3 volt or even 1.5 volts times 4. That would work okay. And well, at least it would go forward, and then once I've wired up these ultrasonic things, at least it could potentially detect some obstacles, and then we would want these wheels, one to go forward and one to go back, so it basically spins like that on its own axis. I'm sure you've seen it in Robot Wars or something like that. But it'd be a good starting point if you think, like, I want to pick up one of these, and they weren't expensive, which I'll show you. Yeah, I think it could be quite interesting, to be quite honest. Right, let me find that device. There it is. So if we go to our browser, there we are. So what we're saying here is £7.67. I can't remember how much I spent actually. It's around about that figure though. So what you get is the 2 motors, the 2 wheels, the battery holder, on-off switch, which is down there in the middle. Turn that off now actually. And oh yeah, the front caster thing. Right, if you notice, the caster thing is being held off now by these brass separators, whereas in the pictures it shows this thing clamped right up top. That's because I think they've given us a smaller caster wheel now. And of course you do want this to be kept level, otherwise all this would be, you know, pointing the wrong direction, wouldn't it? Okay, I think that's probably about it then. So we've seen how much it costs, we've seen the code, and it was all fairly straightforward, wasn't it? And you've learned why we're using an H-bridge to control the direction rather than just a single MOSFET, or indeed 4 MOSFETs per motor, and certainly not a transistor. Right, okay, I think that just about brings us to a close for this one. I hope you've enjoyed it. If you can suggest things that this can be used for, rather than just artificial things. Oh, well, do not suggest, please, that it can be used for attaching to some sort of vacuum cleaner. I've got one of those, and it gets stuck under the television cupboard every single time. It's even got sensors on the top, some sort of wire things. and it says, can I get under there? And it forces itself to go under and then immediately gets stuck and goes beep, 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 help. So pretty rubbish, really. I think this would probably work better. Hey, perhaps I could sell it to them. What do you think? They're a big manufacturer of vacuum cleaners. Okay, that's it. Time to take a break, I think. Hope you enjoyed it, and I'll put all the links and everything else and the sketches and so forth on the GitHub, and I'll see you in the next video. I hope you're finding these videos useful and interesting. There are plenty more videos to choose, and a couple are shown below, and if you'd like to subscribe to this channel, just click on my picture below and enjoy the rest of the videos. Thanks for watching.